Üniversitesi gibi birçok önde gelen üniversitede mimari ve yapısal cam konusunda çeşitli dersler veren MacFarlane, yapısalcı mühendisin karşılaştığı zorlukları gidermek ve kodlanmış pratiklerin rehavetinden sıyrılan mühendisliğin nedenli heyecan verici ve yenilikçi sonuçlar doğurabileceğini, camın iddialı mimari projelerdeki kullanımının artmasını sağlayan cam üretim ve işlem alanındaki gelişmelerden bahsederek aktaracak. Şimdi kendisini sunumunu yapmak üzere sahneye davet ediyorum. Please, sir.
Thank you, Zaina. Thank you, Dr. Atom. I'm not sure what you said, but I'm sure it was nice. Thank you also for coming out tonight. I'm from London, and you know this is normal for us. And all of my friends, when they heard I was coming to Istanbul for a week, they were very jealous as I left rainy London and arrived in rainy Istanbul. It was very unusual. Anyway, I love Istanbul as a city, and it is actually I'm an engineer, so I like numbers. And I like the physical feel of materials. But I also love architecture. And Istanbul, funnily enough, is the city where I had my first experience. As a 20-year-old student, I was touring all the ancient sites and arrived finally in Istanbul and walked into the Hagia Sophia. And it was very moving. And I thought, my goodness, you know, music had always moved me. Poetry, very occasionally, had moved me. Art I found difficult. But here was a space, here was a fantastic dome, and so it was the beginning of, I guess, a dedication of my life in engineering, a dedication to architecture. It is the thing that touches me deeply, but I'm still good at numbers and I still love materials. So, as an engineer, I guess I was trained in a very formal way at university, and I emerged as a student engineer, and I was basically given the idea that I really wouldn't be ready to design anything until I was about 50. So I was surrounded by codes of practice which guided my every move, and I felt wonderfully protected. Then I started my own practice. Of course, I was very dedicated to architecture. I was very dedicated to serving architecture. So when my architecture friends in London asked if I could help them with a glass structure, I was at one level very keen and very enthusiastic because I wanted to help them do what they wanted to do. And on the other hand, I had absolutely no idea where to begin. So I thought, well, maybe I should ask Pilkingtons. I don't know if you know Pilkingtons, but in Europe they're the biggest glass manufacturers, so I thought I go to industry and I will ask if they can tell me what the strength of glass is. Well, it's a fairly easy question. You know, what is the tensile stress of glass? Because being an engineer, I need to know this. You know, if I'm going to stand on a piece of glass, I need to know when it's going to break. Okay, it's quite important. So I went to Pilkington's and they said, "Excuse me?" I said, "Could you tell me the tensile stress of glass?" They said, "Oh, I don't think so," they said. So I was puzzled. I thought, well, what's the secret? But it actually is a secret. Yeah, it's their secret. You know, it's their number. Now, how can they own a number? Well, they do. Why? It's not codified yet, okay? All the people in industry haven't got together and agreed how strong glass is. Well, you would think, well, it's a physical material. Surely they can agree this. Well, the funny thing is, 20 years later, they're starting to develop a code of practice that we can all use as engineers or architects. And they're gathering information from Belgium and from Holland and from France to make the Eurocode. And there's a little expression which says that the strength of glass is equal to the characteristic strength times gamma n. You think, well, what's gamma n? It is gamma national. So that in France, the number is 1.3. In Belgium, it's 1.1. In Germany, it's 1.9. So everyone has their own idea of how strong a piece of glass is. That really blew my mind. That really made me begin to think that dealing with engineering and dealing with engineering materials is a very primal thing. It's a very adventurous thing. It's not something that's already written in the book. And having been protected by the steelwork code and the concrete code and the timber code, here suddenly I was out naked, nothing to help me. And so every step that I have taken in my glass engineering career has been taken with a great deal of caution and sometimes a great lack of sleep. And I know as architects, I used to wonder about architects, particularly as students, because they would stay up all night, sometimes 2 nights, to finish a project. Engineers used to go to the pub religiously at 7 o'clock and come back at 11, work for another hour and go to sleep. So what was it that drove the architect that didn't drive the engineer, that I could see? Well, I discovered it because here I was on an exploration of something that had not been done before, where I was putting myself on the line. And that is good for keeping you awake. Okay? So the journey will start in 1985, and it will start with It will start with an image. This is an image that Pilkington have in their library, and that is a piece of glass, and there are 5 ladies standing on the piece of glass, and it's not safe. Okay? They shouldn't be doing this. The reason is, what happens when it breaks? Well, they'll fall down. And that's the very first and most primary thing that I need to remember when I design a glass structure. It's the primary thing. What happens when it breaks? I don't care what kind of glass it is. I don't care where it's made, how much it's toughened, how much it's processed. There is no glass that we use in the industry that may not break. So you have to think in every single design what happens when it breaks. And that's been really the guiding principle behind everything I've done with glass. So this was our first staircase. This was the one where we needed to find out the tensile strength of glass. It's very simple. It's just a stair tread. We've seen lots of stair treads now, but this was 1985, and there weren't a lot of stair treads then. In fact, I didn't know of any others except Pilkington's did have a solution, but it had a steel frame all the way around the edge. And our architect did not want a steel frame all the way around the edge. And because it was just a little humble architect, and Pilkington's were a very big practice, they're not going to help the architect. So this is why she needed us to help her. So we very gingerly started to think about, if a person stands in the middle of the tread, what is the tensile stress here? And what I found was, amazingly enough, a 1940 engineering handbook. It's very thick, like a Bible, and it has all this wonderful information. And I just thought, I wonder if it's got something about glass. And when I looked in the index, it had 2 lines. But the 2 lines were the tensile strength, compressive strength, every single physical property of the glass in this little, in this big book, in 2 lines. No explanation. Just gave the numbers. Didn't say whether they were safe, whether they were ultimate, whether... Anyway, I took the number, and the number was 70 MPa for the engineers in the audience. That was the number, and so being an engineer, and it being the first time that I did this, I decided to divide by 10. So the number I used to design this tread was 7. Okay. And it resulted in a tread which was 25 millimeters thick, sitting on, and this is the key for the staircase, because you have to say what happens when it breaks. Sitting on, you may just see it, a sheet of acrylic, right, which is hardly visible, but it's a very nice solution. And the same architect is using, after 25 years, she still uses the same design. This is Eva Jurek now. And there's good reasons, because the glass is annealed. Okay? Annealed means it's not been toughened or heat strengthened. And it means when you crack it, you just get a crack. But what it also means is that you can polish the edges, and you can also engrave the top. So even though it's not a strong glass, it is actually a very safe glass. And aesthetically, it's a better glass than the toughened glass. So this is Eva's composition, where she is almost baroque in the way in which she supports the glass with the metalwork. Which, of course, is the other thing about glass, is that the connection and the detailing has to be completely thought through, because it's always visible. You can't hide it. This is another of her staircases. And we've probably done 20 staircases of different types with her over the years. Always the same principle, there you see. Sandblasted surface, obviously anti-slip. Also, if you stand on something that's transparent, you feel uneasy. I don't care. There's very few people who happily walk out and don't feel a little bit uneasy. So, you have a glass tread to bring the light down through the building. There are many other reasons other than transparency. And the other thing is, if it is transparent completely, then it will very quickly scratch. So that after 2 years of use, it'll look like it's been sandblasted. So we've really always thought that a treatment to the top surface that can provide anti-slip and can provide a visual barrier, but is also easy to clean, is very important. This particular one is sandblasting, which is not that great to clean, but it does the other things. But I'll show you one in a minute. This is easier to clean because it's acid etched. This one was completely transparent, and the idea being that you walked from the street across a bridge into the restaurant and could look down. This was 20 years ago. It's still there, but the glass is now completely translucent, so you can't see through it, and that's just through people's foot traffic. But it's survived. It's outside. It's in a street in London, and it hasn't deteriorated. This is the Apple store in Chicago, where we developed a tread which can now free span from side to side without any intermediate support. The reason it does this is that we've developed a laminated solution where there are 4 layers of glass. The top layer is acid etched, and there are metal inserts which are embedded into the laminate. You can just see the ghost of the puck there. So basically these 4 sheets of glass plus the puck go into the laminating oven, and when they come out you can then attach them to these metal pieces which are then attached through to the wall. The whole structural performance of this tread depends on this material here, which is a very strong laminate. It's called Sentry Glass. It's produced by DuPont, and it means that you can really go through what happens when it breaks. So you can break all 4 pieces of glass, and then you can load with a full live load for as long as you like, and it stays in position. So the whole structural language of glass has now opened up in such a way that you can do what you like, really, as architects, in terms of scale. It's probably not what your client would like, because it's quite expensive. Okay, so you can do interesting, beautiful glass. For example, the glass balustrades on the staircase here are chemically toughened, which means that they go into a bath of fairly toxic, dangerous chemicals, but when they get strengthened by that process, they don't buckle and they don't bend. So you have this perfectly curved and geometrically perfect piece of glass, which we need for the structural connections. But each of these staircases for the Apple stores costs about $1 million. So you probably don't have too many clients who are ready to pay that amount of money. Just to go back to this for a minute. The process of making these panels is that you heat strengthen the glass in an oven. You then laminate it together, and then you put it into an autoclave. And 4 years ago, 5 years ago, the maximum size of a piece of glass was about 6 meters by about 3 meters. We now have a German company called Seele, who fabricate all of these staircases, and they can do 15 meters, which is a big piece of glass. But lo and behold, the first Apple store in China is in Shanghai, and it's a glass cylinder. And Apple insisted that the glass be sourced in China. And we've actually found a glass company in China who can make, now, they can make a piece of glass 18 meters long, which they can curve and which they can laminate. So there's virtually no limit, I should think, to what you want to do architecturally in that sense. I mean, given it's a flat material and you can only bend it, you can't actually pour it like concrete, but given those limitations, I think structurally your other limitations are now almost gone, and you can do lots of things with them. But in the early days, back to, again, 1989, Iva Jurikna was all about the connection and the metalwork as well as the glass. This architect, Rick Mather, his whole concept was to actually build the glass without any connections. Okay, so he didn't want to see any metal. And when we first looked at this, he didn't have a glass beam, he had a little metal beam over the top and a little metal column. And when we were discussing it, I suddenly came up with the thought that maybe we could do this as a glass beam. And of course he got very excited. He said, okay, let's do it. And then I stood back and thought, wait a minute, I'm not sure if I know how to do this, I've suggested it, but I need to think very hard. I'm suggesting a glass beam above your head, and, it's dangerous if it breaks. And you think, well, glass might break. And anyway, I thought about how to make it fail-safe, and I came up with the idea of, okay, put 2 pieces of glass together, and that will make it safe. And then I thought, well, why not put 3? So that then became the basis, really, of using laminated glass as a way of providing a fail-safe structure, so that you have a laminated glass column, you have a laminated glass beam, and they intersect a little bit like a timber connector. We got to the point then of saying, okay, we've got rid of the steel here. We want to put an insulated glass roof panel, and we want to put an insulated glass wall panel. And if you look at an insulated glass unit, it has a big metal piece in the edge. So we finally designed these panels to have a glass spacer in the edge. And there was a little concern about if the moisture got in, would this cause a problem? So we ended up with not only glass beads here, but actually a heating element like you get on your car windscreen, so that on your rear windscreen, if you want to get rid of the condensation, you put a heating element into the glass. And the architect then did away with the radiators, so that the whole structure is the radiator. So the glass is completely glass, and we have a radiator for the window. This is the bigger version of the same technology. It doesn't use the heated glass, but it does use glass with a ceramic frit, basically to reduce the sunshine. As I said earlier, we don't get a lot of sunshine in England, so that's probably just as well, because glass lets a lot of heat into the building. Now, one of my engineers, he went to Japan to live. And he called me up after he'd been there for a couple of years, and he said, we have this glass problem, and we wonder if you could help. I said, okay, what is it you want to do? And he said, well, we want to build a cantilever in glass, which is 10 meters from here to here, and we want to do it all in glass. And I thought about it, and then I thought, wait a minute, he's in Tokyo. And as we know, Tokyo shakes, a bit like Istanbul shakes, but we don't shake in England, so we can build glass structures to our heart's content, and we don't worry about everything moving. But in Tokyo, this was a different issue, and I thought, wait a minute, no, you don't build a glass structure in Tokyo. So I basically thought he was a bit crazy to suggest the idea. But then about a week later, the architect for the project called me up from Tokyo, and he said, I hear you're thinking about our problem. So I thought, okay, maybe I'd better think about it a little. Anyway, in thinking about it, I came up with the idea that I couldn't, at that stage, get a 10-meter-long glass beam, but I could get pieces up to 5 meters long. And I thought, if I can overlap them, then I can reduce the force in the connector, which was the big thing to do. And the thing is, I didn't know at all what load this could take. So I got my glass fabricator to make this very simple piece of glass as a test equipment. Then we put the glass inside and between these two steel channels, and then we basically loaded here. So it's a very, very crude experiment, but told us a lot. In fact, what it told us was that the force in that bolt, and it still didn't break, was 6 tons. So we had 6 tons of loading in this point here, and I had estimated here a maximum shear of 1 ton. So I knew that there was a good chance that we could actually achieve what we wanted. Now, I guess there's a lot of architects in the audience, and as architects, you know the power of the model, right? As engineers, we know the power of the number. And when I came up with that solution, a couple of architectural friends visited me that night. They wanted to discuss a glass thing. And I showed them the idea, and they got really excited, and they said, oh, it's a great idea. And so I then got more enthusiastic and thought maybe it is really a good idea. So I did the numbers and the drawings, and before I went to Japan, I went out with the idea to Japan, they gave me this little box, and they'd beautifully lined it in true Japanese style with sort of nice velvet, and they made a little model of half of the canopy. It's actually got 3 beams. And you can see it demonstrates the way in which the load goes back down to the base. And I took it out to Tokyo, and it was really what made made them believe that this could be done. I mean, it was a big jump at that stage because nobody had any idea how much load these things could take, how it would work in a fail-safe way. We didn't really know either yet. But we kind of believed it as well. And being British, you know, we do things on a shoestring. You know, we're not very organized often. So we had come to the conclusion that we could make this structure. I needed to know the cost as well. So we even went with a cost, you know. We can do this thing, and it will cost you £180,000, right? It's about 400,000 your currency. And that was to do the whole thing. So we got there, and we started to talk to the client, and they said, yeah, very good, we like the idea, but we like to give you £80,000 to do some testing. We said, what? We'd never, ever had that sort of response in the UK. I've since found out that what the Japanese do, which I think is very clever, is that the main contractors get together every year and they decide which architectural projects or which architects they are going to support. So they might say Tadawando's building. They give them up to 5 times a normal building budget to explore Toyo Ito. You know that building with the columns, the inclined columns? He got 5 times the normal budget to look at the welding issues, the whole thing. And that's the way they move things forward in their industry. That's the way they move their technology forward, which I think is absolutely brilliant. Because otherwise, with buildings, how do you do it? You know, a building is not a car. You know, with a car, you can spend a fortune designing the car, and then you make, 50,000 of them, so all that research is done before you do the thing. I mean, we are in a different position designing buildings because every one is unique at some level. It may look like one, but the site conditions are different, the loading conditions are different, all kind of things are different. So each one is unique. And this makes a big difference, I think, in the way in which we can be creative and the rate at which we can be creative, which is limited. Anyway, they gave us this money, which was brilliant, and we made this first blade, which is about 5 meters long. And it's funny how standards creep into things, because everything had been designed in the glass industry to be within 2 millimeters, plus or minus 2 millimeters. That was the standard. Now, our design demanded that these holes be exactly where they should be. And this machine here is a CNC machine. Okay, so a CNC machine, it cuts to 0 tolerance. So we spoke to the glass fabricator and we said, we need this glass, we need you to cut it to absolute tolerance. He said, no, I can't do that. Well, why not? He said, no, this machine cuts to plus or minus 2 millimeters. We said, that can't be right. So we spoke to the metal guy, and we said, he says his CNC machine cuts to plus or minus 2 millimeters. He said, no, he just doesn't know how to use it. He never needed to use it for anything else. So we tuned this machine, or at least the metal guy tuned the machine, so that it cut these accurately. Now, the Japanese were a bit upset, actually, because they really wanted to make the glass. But the funny thing is, they didn't have a machine that would allow the glass to go in at the length that we needed. So this was the oldest machine in England, apparently, but it had an open end and could allow the glass to be processed. So we had these Japanese Asahi engineers all coming to London, and You know, in Japan, everything is also beautifully organized. You know, they're very Germanic in the way that, you know, everyone dresses in the right, you know, they've got the telephone here, the safety harness. We're not like that in England. I guess you're not really like that in Turkey either, but we're kind of similar. The people in this workshop really don't look like organized, you know. They really don't. So we were bringing these engineers further and further into the industrial part of London, and their faces were getting longer and longer. And then we came out, and I think they were rather shocked at the state of the works, you know. But they knew that they guys couldn't do this accurately. So the first thing they did was they took their tape out and they stretched it between the holes, and there was this wonderful moment when there was, ha, ha, you know, because it was absolutely bang on. They were completely shocked. How could this come out of that, you know, was I guess their thought, which is not unreasonable. But, you know, once you get people directed in the right direction, you can achieve a lot. This was the test that we did on the glass beam to prove how strong this was. Remember, I needed it to break at 1 ton. Anyway, we put a bolt in here and we specified a high-strength bolt for the test. And basically, you hold it here, and then you pull down here. Anyway, it broke suddenly, bang. And we all went over, and it wasn't the glass that had broken, it was actually the bolt. Straight through. And the reason the bolt... The technician who'd put it together, we'd specified the high-strength bolt, and he didn't have one. I thought, well, it's glass, you know, what am I worried about? So he just put a normal, mild steel bolt in it, and it went right through it. And it actually broke at 12 tons, this piece of glass. 12 tons, that load there. So we were very satisfied. We had a very big factor of safety. This is toughened glass. You can see the way it breaks into tiny little pieces. And see? Perfect uniform. See? Little belt here. All wonderfully coordinated. Fabulous to work with, you know. I love the whole Japanese way of ritualizing everything and getting it more and more perfect. I know for this piece here, the stainless steel barrel at the bottom, the man who was making it, you know, he brought it round as a sample to show to the architect and the other Japanese contractor. This is like an offering, and he's, ha! And they went, you know, they chased him away, you know, so he runs away, and he comes back the next day with another offering. And he did this about 4 times until it was almost absolutely perfect, and every weld was done perfectly. So they were fabulous to work with, but they were also curious, you know. The thing that you're looking at there is not glass. It's acrylic. It doesn't need to be there, but it's there because the engineer from the contractor, he liked that staircase with the acrylic underneath. He thought that was a good idea. He thought, glass breaks, acrylic holds, great. Now, we had a factor of safety of 12 on our glass. We tested it. We were absolutely clear. All the sheets were laminated. Everything was fail-safe. And this little Japanese guy, who had said nothing for 6 months, he used to come to all the meetings, and you know what you do when someone comes to your country, you take them to the nice restaurants or whatever. He never ever said anything. Then finally, when we were just ready to go, he finally cleared his throat and said, I would like acrylic. We all looked at this guy and said, what? What do you mean you would like acrylic? And he said, I want acrylic. And so we had to change the whole design to sort of make it wider and whatever, to put acrylic beams as part of the assembly, and you can just see the edge of them. And the only thing that's really nice about that is that he then insisted that the edge of the glass, which is the most beautiful bit, you know, where the light comes through, he had to put aluminium on the edge. Aluminium strip. We said, well, you know, why do you want to put an aluminium strip? In case someone hits the beam with a hammer. And we said, what? In Japan? I don't think so. You know, in Scotland we do that, but in Turkey, I don't know if you do that, but in Japan they don't do that. Okay, they don't go around hitting things with hammers. They're very, you know, civilly obedient. So anyway, this was our acrylic in here, and this was our aluminium. But nonetheless, I thought it was great that they actually did it. I thought it was such a sort of exciting adventure. And there are lots of stories of getting it over hurdles and getting people to approve it. And it's very, very stiff. We wanted to do a photo shoot with the big wrestler guys, you know, on the end, sort of one on each beam. But I think the wrestling thing is a kind of a religious thing, so they didn't think that was so funny. You know, we thought it would be a nice picture, but they didn't do that one. Anyway, this is another bolted glass assembly in Saudi, and it's also using glass by stacking one piece on top of the other, so that the whole thing has got no visible connections on the outside. It's all siliconed, which is the other magic material. Okay, there are three magic materials. There's glass. That's the most magic. There's that interlayer that I talked about that we did the Apple stairs with, which is Sentry glass. Okay, it's an ionoplast interlayer. It's fabulous. You can actually stick metal to it and do all sorts of nice things. But silicone is a fabulous glue also, because it gives and negotiates, but it's still got nice, sufficient strength. So if you only were given three materials to choose from, please choose those ones. Do not choose thin glue, okay? We've had endless issues of trying to use that in our structures and never been successful. But you can see this crazy pane here? It's not really a pane, actually. That's a line that's drawn across there and there. The pane is actually like that. But the architect wanted to see it as a sort of 3x3 panel. But basically, the glass is stacked, and the connections in the middle are joined with friction connections here. Clamped glass. And that's the load test, our engineer. So these are two-way spanning structures. This is its completely independent, freestanding, slightly bigger brother, which is in New York in 59th Street store for Apple. And it's using a very similar idea of glass fins and glass beams. And this is the model. But there's one interesting device which we used in the roof, which, if there's engineers in the audience and you haven't seen reciprocal beams working, I really hadn't up until this. Basically, that's an individual beam, and then that is an individual beam, and that is an individual beam, and that is an individual beam. So none of them are continuous, and they all just go one onto the other. And it's a party trick. I need a knife, but 3 glasses and 3 knives, and you can cross the knives in the middle, make a little triangle, and stand the glass on it, and that's reciprocal beams. And I think it's got fantastic potential, because you can use very simple 4-meter long elements, let's say. It could be aluminium, it could be steel, it could be glass, it could be wood. And they're all very simply connected. So it's just a little, one just bears on the other. It's only a shear connection. So it's very easy to achieve. And I think there's a lot of structures. And it can go on forever. It can keep going, you know, like span this whole roof. I mean, the beams get a bit deeper, but it's always still just made up of pieces. So I think with glass, it's good because the connections are always the tricky one. This is still too complex, really, for me. I'd rather it were a bit simpler. Here you can see now we've got 5 laminates. 5 laminates. You can see this one stops. It's like a timber joist hanger. And this is the formwork for it. These are embedded in the glass, laminated into the glass. And the funny thing is, Steve Jobs is obviously the client, or was the client, and his obsession with everything that came out of Apple meant that also all the glass structures for the Apple stores he personally not only took an interest in, but controlled and managed, as he did with the iPhone and the iPad and everything else. And the one thing that he did right at the beginning, when we designed the staircase, I was in my apartment at the time, and I got a knock on the door, and FedEx delivered from a lawyer the patent documents for our design. Like, what? You know, what does this mean? And, you know, it was the way he's a product person. Okay, and with product, you need patents. You need to protect your investment. But it's very different with architectural design. I said, well, I don't care, you know, you can take the patent all you like, because I'm never doing that design again. We'll do something different. You know, the next architect doesn't want to do an Apple store, not if they're worth their salt. They want to do a better than Apple store, you know. So the idea of patenting architectural design is nonsense. It doesn't make sense. Every time we do something, we progress, we move something forward. It's fine for product, but not really for creative thought. This is the Tickets Pavilion in Times Square, which I think is still the biggest glass structure. It doesn't really look like it, oddly enough, because it's got things underneath that catch the rainwater. Underneath this big glass staircase, there's actually metal trays, which are not structural. They catch the rainwater, but the whole transparency got lost. That's when you don't have an architect in control who's in control, right? He wasn't in control. The original design architect was in Australia. Executive architect was realizing it, didn't quite manage it. We had lots of discussions about what the tread should be and the color of the tread. And these are the final load testing, our engineers there. And so there's the glass beam, and there you can see the tray for picking up the rainwater aluminium tray. And there the treads are laminated, colored laminate. And this is the ticket booth going into Times Square. And this is a strange incident where we just erected the middle glass wall, and a taxi driver came through this fence here and crashed just before it, just in the front of it. So we hadn't anticipated at the time, but there are now a series of traffic bollards there. He had a heart attack or something, you know. But there's a movie which was made at the same time. Can't remember what it is. It's got Will Smith in it. And it's about when New York, there's a disease there or something, and everybody leaves the city. And they set it in the future. Okay, so they said, what will be in the future? And they found out we were making this. So they built a stage set version of this in their studio. And here's the irony. They spent $2 million more on their stage set than we were given as a budget to build our building. Which is not fair, is it? Anyway, we did finally build our structure. And there are these aluminium things again. You can just see there's the glass coming down there, stepped. Using the same principles as the Tokyo canopy, overlapping the glass, spacing the bolts. And basically all the light should have been coming through the top at night, going out the other direction from lights inside, but I didn't quite like that. But there's a great... I mean, my son, who's 13, is really not interested in what I do at all, right? Except that Alicia Keys did that song, New York, on this, and then he clicked that I actually had something to do with this, you know, so I became his hero for a week, at least. There's a great video, if you haven't seen it, of Alicia Keys standing there. Now, these panels here are flat glass panels. They're about 4 meters high, and they support all the glass beams at the end there. You see, 4 pieces of glass together. So very, very structural material we're talking about. This was our first big job when we got to America. It's a performing arts center. And the one thing the architect wanted was these end walls to be very transparent. So we came up with an idea, which was to have vertical cables suspended from an arch here and tensioned by cast iron weights, so that you actually don't need to stress the cable. You just simply attach the weight, attach it to the arch, and attach it to this piece at the bottom, so that when the wind blows, the cable rolls out, the weight goes up, and when the wind stops, it just drops. This is a study of the wind pressure on the wall, because we were a bit worried about the wall moving in and out, and this is the construction. Now, this is probably the one project where I really realized what it is that we do. I mean, as engineers, what we do, right? So you've got to listen carefully, and if there's any clients in the audience, they should really listen carefully. Because I must say, you get, after years and years of working as you work, you just do it, don't you? But with this one, here we were given a design problem. Okay, so we solved the design problem, and we solved it in that simple way. You know, we have a cable, you have a weight, and then you just attach the glass to the cable. Simple. So we called in 3 major contractors and we said, here's what we want to do. And they said, yeah, sure, I think that's okay. So we put it out to bid. The 3 contractors came back and they said, we can't do that design. We said, well, what do you mean? You know, you've already seen it. What's the problem? And they said, well, we're not sure that it works. I said, well, I know that it works. They said, yeah, but you're not taking design responsibility. Right? Because in the glass world, that is still mainly the way it's done. The contractor takes design responsibility, and I, as the engineer, just give him a picture. Can you do this? Sure. So he couldn't take responsibility for something that he didn't understand. And that's not unreasonable. Why should he? It's not unreasonable. But we thought, well, how do we solve the problem? We were stuck with a budget which was 2.5 times what we thought this should cost. We had designs which were nothing like we'd designed and were not elegant. So what could we do? And then someone said, well, look, I know a local glass contractor. Why don't we talk to him? So we talked to him and we said, you know, you need to build the arch and hang the cables. He understood all that. Yeah, I could do that. And he said, but it's too complicated. We said, well, what's complicated? He said, well, I don't understand it. I said, well, you don't need to understand it. Just build it. We understand it. We'll take responsibility. So we got the wall built for the price that we originally thought, which was a third of what the market was going to hang up there as sort of chic glass, by taking design responsibility. It's an important thing to remember, because you cannot do an innovative design and give it to the contractor and hope that he'll take design responsibility. That's not the way that you will innovate anything, you know, because they won't do it. But if you're able to actually take the whole thing through, specify it and take responsibility, then you can get something which architecturally is right for the building, something which explores and advances the engineering in the building, and client listen, something that costs a third of what the non-innovative solution costs. That is very important to know that innovation does not need to cost money. And this is the process of putting it up. There's the cables. They're about 30 meters long, and the glass very simply held on the corners. That's the detail. And these are the weights, which are just above the dining tables, so you can see the weights go up and down in the wind. I mean, it's basically designed to deflect about a meter in the middle, you know, about that much. Which seems a lot, but it's a very big wall, and a meter doesn't actually bend or deflect the glass so much. I mean, the funny thing about glass is it's very bendy. And if it's heat-strengthened glass or toughened glass, you can bend it a long way before you break it. And this is the roof, which we also designed, basically Verandil structure, with the glass coming right down onto the structure. And the thing about parallel cables, rather than tennis racket walls, is that you can actually go around corners. So you can take the whole glass wall on a curve easily. This is another project that we did in Japan, which is an entrance pavilion for a museum. And again, great Japanese mock-up. You know, they examined every single bit of it before they built it. And as I was saying earlier, it's very important with glass design that you really design these pieces. These are all designed, they're not from a catalogue. You know, you need to find the metal guy, and you need to design each of these bits. That's the this is another curved surface created with straight lines for Kew Gardens in England. See there. This is also a design where the glass, each piece of glass, is actually sitting on the one below it. Right? It's not held at that point. If you held it at that point, it would mean that that bracket would become much bigger, and it would then also mean that the cable itself would become much fatter. But if you can support this piece on this piece, you can get a very clean design. See, that bracket would probably become twice as big. Now this is taking the idea of the weight acting over a lever arm to tension horizontal cables here. So it doesn't matter how much the building moves or how much the wind blows, the weight will always adjust to support the glass against lateral loading. And again, the glass is stacked from the bottom, so that piece is put in first, that one is then set on top of it, that one's set on top of it, and that one's set on top of it. And you might say, well, what happens if this one breaks? Well, basically, the silicone in the joint is strong enough to support that panel of its adjacent neighbors, even with that gone. So you can replace this panel, and all of those will, in the short-term condition, stay where they are. And they kind of wanted to expose these weights so that you can see them going up and down. Now this is a little example of, again, the elasticity of glass. It's a roof light which is that shape, and the length of the beams as you come round the corner changes, but the glass always starts and finishes or always starts at the same level and then finishes at a different but same level, which means that the slope of each beam becomes slightly different. So there are the glass beams. And the beams are actually sandblasts so that you get this striped effect. This is a wall that we did earlier, but it's using the same idea. So there's the problem that we ended up with. We had a glass beam at that slope and another glass beam at that slope, and then you have to put a panel of glass in between, and you end up with a piece of glass which needs to be warped. Okay, so that's at one level, that's at one level. And this fourth corner needs to be pushed down. And when we examined this, we'd completed the design, and then we examined it, and we realized that the corner needed to move by about 6 inches, which was shocking, because everyone suddenly thought, my goodness, we're going to have to bend every single panel individually, which would have been very, very expensive. So we finally persuaded the client to do a sample, and this is the sample to experiment. It's an insulated glass panel, so there are two pieces of glass, and this is the force that is needed to bring this corner down. This one's the same level, this one's the same level, this one's the same level, and this one drops down by 6 inches. And there it is, and the glass doesn't break, which is pretty good, really. So they could build this roof from flat glass, and then, you kind of hold that one down, and then you stand on that one, and then you bolt it down, and you create the curve, which is one of the surprising aspects of glass. You tend to think that you couldn't really do that, but you can. Now with grid shell structures, the first one we worked on was the library in Seattle, where basically the quantity surveyor for the project, the cost consultant, was a bit alarmed that the costs were escalating very, very high. And the grid shell, which had been proposed by Arabs, was a steel member, 300 millimeters going this way, and then another one 300 going this way. And then they had a big gap of about 300 millimeters, which was for tolerance. Then they had a whole other system of rectilinear glass on top of the steelwork. And basically you had 4 systems, and the wall was about this thick. And it was costing about $24 million, which was too much. So we looked at it, and it's the advantage of having a sort of structural understanding of glass and a structural understanding of steel was that we actually brought the two things together, and we had Sealit in Germany, who were probably the best contractor we could find, who put a bid in for this project at $12 million. So they came in at half the price of the American contractors, built it in a much more simple way, and built it very precisely and very beautifully. This is their, well, it wasn't their steelwork, but it was their cladding system. So it would have looked very different, I think, if we if we hadn't come in. And I guess, again, it's achieving, through design, achieving efficiency and, I guess, elegance. I mean, maybe Coolhouse actually liked it to be, 4 foot wide. I'm not entirely sure ultimately. But and this is the project Dr. Atom was showing earlier of the Shenyang project, which is where we met ERA. They introduced us to this project as peer reviewers. It had already been designed, and it was a wonderful opportunity to find out about China and about how they do things in China. I was always kind of terrified to go to China because there were so many horror stories of people doing design for nothing, people not being paid, and it didn't seem attractive from that point of view. But here we had great luxury because we're with a Turkish architect and a Turkish client, and we had the opportunity to see how things worked there or didn't work. And I mean, the grid shell roof is a really ambitious thing to do, this doubly curved surface, and there's only 3 or 4 of this scale in Europe, and they've only really been around for the last maybe 8 or 9, 10 years at most. And so we kind of expected, well, it's got to be someone like Wagner Bureau or Sealit or one of these guys who's going to build this thing. No. It's the Chinese are going to build it, right? And they had this facade contractor who won the project, and he was responsible for the steelwork. So we said, well, who's your steelwork fabricator? He said, we bring him in. So we said, well, how are you going to go about designing the connection? Where all the steel, this here. How are you going to design this? He said, we have a big pipe. He said, big pipe. So he was going to put a big pipe at every node and then bring all of the members in and weld them to the big pipe. So it would have looked like one of those, in science you used to get those atomic models. It was a bit... so we said, well, I don't think you understand what needs to be done here. So we said to the contractors, the facade contractor, we said, this guy he's not the right guy. He's never done anything like this. He said, I go look again, and we were kind of despairing. And then this character turned up. He was a little professor, high, sort of bald head, and he comes in. And I knew from the instant he walked through the door that this guy had something. Anyway, he started to talk, and then he showed what he'd done. And he'd done all these beautiful grid shells at the Chinese Expo, if anyone was there, on the entrance pavilion. Big things, you know, they were about 80 meters high, 90 meters diameter, and beautifully made. And so we thought, yeah, and there's a wonderful bit at the end where he's being interviewed by someone from the BBC, and he has this little clip of himself being interviewed by the BBC, and he was so proud of having achieved building these within the time frame and really beautifully. He starts to cry, you know. He's like, and you think, well, this person might actually be the right person. And they gave him, I mean, they're nuts. They sort of said, okay, you got to start on the 15th of October, and it's got to be all finished by the 15th of December. All finished, all built. And he's got to design it first. I mean, it has been designed, but he's got to then go and do his own design. And he says, yes. You think, what? This is impossible. So you go to his factory, which we did for a visit, and it was like a Sunday. And of course, there was nobody there. And it looked like nobody had been there for about 100 years. You know, it was all thick with dust. And he'd been telling us that, you know, he had these special CNC machines that he'd invented for making these very precise nodes. And I said, where are they? You know, and there's this kind of Heath Robinson invented-looking pieces. I thought, oh my God, have we done the right thing? But, you know, we went back about 4 weeks later, and you could hardly get in the door of the factory. There was sort of Chinese cutting metal in every corner, and you know, every little bit of the factory was being used, and they were doing things by hand. And then you saw these CNC machines. It was like Blade Runner, you know. It was like these things came to life, and they were beautifully, technically brilliant. And he took up the challenge. I mean, in the end, he didn't have to finish it as it so happened, but you know, he was willing to, and he got a long way there. I think by end of the period when winter comes and they can't do it anymore. But it's very interesting also. You know, it's like, blimey. You know, you have to hand over all your design there after scheme design development, and you've got to give it to the Chinese, and they don't speak to you anymore. They really don't. They just get on with it. But actually, they don't really get on with it. They get on with it in a funny way, because this guy doesn't talk to this guy. You know, so you say, have you looked at the detail where this comes into here? Oh, we'll sort it out on site. And, you know, you get to site, and this bit's low, so he goes in, he cuts it all out, moves it up, welds it all together again. And it's a very strange thing. It's like everyone gets on the train, and it's like the dictatorship that it is, you know, that there's one idea, there's one person, and we're all going there. And it's hilarious watching. I mean, it's a bit sad, but, you know, as an architect or a designer, you're actually trying to influence this. And they're nodding their head in that sort of Japanese do this as well. Yeah, and you think, oh, right, they really understand. They do. They understand what you said, but they don't agree. But they're not going to, you don't know that, you know. They just, you know, go their own direction, and stopping them is pretty hard. You've got to tell them there's something structurally major wrong, and then they pull up, and then they listen, and if there is, they change it. But don't think that you can change the color of anything, because that won't be on. You know, because it's the other famous one. It's against the regulations. That's a great one. You can't do that. It's Chinese regulation. Can't change the color of the paint. Chinese regulation. But really interesting, you know, really watching a country that is so energized. My goodness, you know, they're just so willing. They can do. And you can transform it. Like I said about the Chinese company, they're making these big bits of glass. They're making it better than the Germans. You look at this stuff, and it is beautifully, beautifully made. And you think, well, you know. and Mr. Gridshell here, I really love the guy, because he's hilarious. he'd go on and on and on for about half an hour telling us stories. And then he'd take a big deep breath and he'd say, now I'm going to tell you the truth. We kind of look at each other and think, what's he been telling us for the last half hour? But he's so inventive, creative, and he's got all sorts of ideas about making cladding for doubly curved surfaces in an interesting way. So I'm really quite excited at finding within China. There's a lot of potential. A lot of things can go good. So this is the very big, about 16,000 square meters in total. And I think once everything else is there, it will look quite spectacular. And just quickly, another example of load-bearing walls, and probably the first one that we really did, where these panels are holding up the steel roof, and we've got little springs here to shed the loading. If we lost any panel, then it would go on to the next one. So it's got a lot of fail-safe in it, basically. And all to achieve, a corner with no column, really. I mean, being an engineer, we'd put a column in the corner, wouldn't we? It'd save a fortune. But the client was very rich and wanted to see the beautiful Santa Fe countryside. And I guess that's a nice thing. But at a more practical level, this is an observation tower for control tower in an airport. And these are about 4 meters in height, about 2 meters here. And the architect wanted no mullions and no columns in the structure. So the whole structure was to be completely held up by the glass so that they got a complete view all the way around, 360-degree view. And we achieved that by building the glass into steel channels, fixing it for the engineers in the audience. If you fix your glass at the bottom and you fix it at the top, it reduces the deflection by a factor of 5. I was surprised. I mean, I've been engineering for a long time, but when I looked at the number, because the big thing about the glass is its deflection, okay? So because, they worry about the edge seals. These are insulated units, and those edge seals which keep the gap from water getting in, they won't put a warranty on that if it deflects by too much. But if you can fix the glass at the bottom in this channel and fix it at the top, you actually get a system where you can use very thin glass to achieve. And we did tests on this thing. It was amazing. You get the glass, you're loading it up, and nothing's happening. And then you get a hammer and you smash it, because you've got to do that. What happens when it breaks thing? And it's still doing it. It's still carrying the loads. This is heat-strengthened glass. Toughened glass which breaks into tiny little bits. Actually, when it breaks into tiny little bits, it's not worth a lot. It's really structurally gone. Heat-strengthened glass, which is not as strong in its normal condition, when it breaks, there's usually maybe just one crack, and it will stay there. So heat-strengthened glass is actually, even anneal glass, in many instances, is better than the strong glass. And this one's heat-strengthened glass, and really, we really did smash away at both sides, and it performed exactly what we thought. And just a little bit of color. We do a lot of art stuff, which I haven't shown in this thing, because it's not necessarily technically advancing stuff, but it's nice to do it. And this is using dichroic film, which splits the light. And this is a daft bit of museum piece where these cars are actually bolted and cantilevered from sheets of glass which are cantilevered from the ground. And it really is an amazing material. Very surprising. I got turned on to it when I was a student, actually, because I did a thesis on glass-reinforced plastic. So I was looking at glass, and there was a book called The New Science of Strong Materials, and in it they said glass, if it wasn't suffering from these little micro fissures in the surface, is about 3 times stronger than steel. And that grabbed my attention, you know. I thought, wow, that's amazing. Because if you take a piece of steel and pull it, it'll go like chewing gum, like that, right? Which is good if you design a structure, because it means that your structure can move away from the load, you know. So steel is quite nice for that, yielding. With glass, when you pull it, you keep going way up above that line before it finally goes like that. It does go like that, but you never witness it because the glass always has a flaw in it, which means that it always breaks somewhere up that line, right? Which is why it's always elastic, which is why it's the perfect engineering material. It doesn't do anything funny, just breaks. But it doesn't do anything from an engineering point of view that is unexpected. It goes, you know, straight line, bang. It doesn't suffer from plastic yielding, or if you push a piece of glass, it'll always come back to where it started. And so it's a very true structural material. Funnily enough, having thought at the beginning that it was a rogue material, it's actually quite extraordinary, and it keeps on revealing itself. That's the other thing. You know, because the industry was moribund for so long in terms of design ideas, locked up in industry, developing production ideas but not design ideas, there's a lot more that I think, a lot more still to do, you know. And I think with the architectural ambition, then I think who knows what's coming next, but I know it'll be exciting. So if you're out there, you're doing architecture or doing engineering. If you're doing engineering and haven't done glass before, be scared. That's all right. It's exciting. And learn and find out. There's a lot more work out there now than there was when I started. And there's a lot more literature, so you can feel a lot safer. And you'll find that you can do a lot. Century glass plus laminate, glass and silicone, okay? That's your ingredients. And so now you must use them to do something. Okay, thank you very much. Sure.
Thank you. Thank you, Tim. Değerli misafirlerimiz, şimdi bir genel değerlendirme ve soru cevap bölümüne geçiyoruz.